Okay, here is a little brainstorming session on the creation of a unit. Previous day in physics class, we did a virtual lab with wave on a string, and the worksheet with some student work is attached with that. The main point was to show that changing the amplitude did not change the speed of the wave, changing the frequency did not change the speed of the wave, or changing the period of oscillation did not change the speed of the wave. Thus, we are going into now a lesson on the speed of sound. In order to do a lesson on the speed of sound, personal prior experiences, harmonic oscillators, and wave on a string. We did 2 experiments, well 3. We went outside, and this was my car. My car is blue, so I'm going to color it in blue. And in the car we had 2 microphones. 1 laptop, 2 iPhone. We had the laptop and the iPhone sitting in the passenger seat of this car so that my AC adapter in my car could power my laptop. We then honked the car horn. Honk. And recorded the sound on the laptop and on the iPhone. Let me make this a little bigger since I'm not sure what resolution we get. We honked on the laptop and the iPhone. The problem with the laptop and the iPhone is that we can't hit start recording at the exact same time, so we have to sync this up manually, which is going to be a fun activity. We're going to do it on paper because the students are not familiar with the audio program that I'm using, and on paper they can be a little bit more physical, and that has been good for those students. So we make a honk, and we use that to synchronize the 2 microphones and audio signals. After the honk, a student runs 30 meters away. And this has been previously measured out to be exactly 30.00 meters. Once the student's there, he waves, and we make another sound here. The first experiment was another honk, and then by determining the difference in time between the audio hit, I mean difference between the start of the horn for laptop and iPhone and the difference in time, and then when it reaches there's going to be a difference in time. It's going to be a very small difference in time, so they've got to be pretty good about figuring out when the audio is actually hitting. I'm looking at experiment 2 right now, which is where the honk, and then about 20 seconds later there was a yell. This is partially so we can get a nice distribution of frequencies to determine if frequencies change. Different frequencies have a different speed of sound, or if different frequencies, some get attenuated more through the medium that it's traveling. Some students were interested in seeing if a harmony, so everyone yelled actually in quite nice harmony. So we can look at then the fast Fourier Transform, the spectrum analysis, to see how that changed things. The third experiment was a very high-pitched noise made with a basketball hoop. That is probably actually going to be the best for getting the speed of sound, because it's a very sharp, high pitch, and narrow waveform. But now let's look at the data that I'm going to produce for the students. Alright, so now I'm going to the program Audacity. Okay, let me get this looking a little better. Alright, so on the top is the recording from the car. I'm just going to play that so you can hear it. Okay, so that was pretty good. Some silly students, but gotta love silly students. So I'm looking here, and I think this it's highlighted that area because I thought I heard the car horn there. And there's the car horn. So I'm going to zoom out and delete everything to the left of that. There we go. So that now let's just make sure we are starting with the car horn. Now I'm going to do the same thing with the other microphone. Zoom out. It's hard to figure out just by looking at this what the car horn is. Maybe it's this one, but no, I think it's right here. Okay, so looks like our honk was right here. Let's investigate. Zoom in on that honk. Yeah, there's the honk. So again, I'm gonna just take everything. Oops, that's what I want to do. Take everything to the left there, and where'd my cursor go? Everything to the left of there and delete it. So that now we can try to match up the starting point, which students are going to be doing on paper. But I want to know what's going on exactly so I can help them with this. Zoom in here. Now it's hard to pick what the start is here. So one thing I'm going to do is I'm going to analyze the spectrum and make this kind of a Fourier transform. Too many points. Okay, so we see over here this is kind of noise artifacts, but over here we get a peak at 707 Hertz. So I'm going to save that image because some students are interested in seeing how these different frequencies propagate through the medium. And that's great. I love when students ask about that. So I will provide them that data. Alright, now I want to look at the waveform from the other device, the iPhone. And it should be very, very similar. Notice it's not, because the microphone's in a slightly different place, and it's a slightly different type of microphone. So these are possibly confounding variables, but the biggest peak here, we've got a, where is that 703 Hertz peak? Is that the same? Is this the honk? No, that's not the honk. So I was looking at there and I didn't see the 707 Hertz peak, which is good. That's a way of testing. That's one thing I'll use actually on the students, is if they're not sure whether a waveform is the right one, we're going to look at it at the frequency analysis. So now I'm going to look here and see if I can find that 707 Hertz peak spectrum. Right there, 707 Hertz. So that's the honk. Confirm, play the honk. Very good. Now, I've got to line these up really perfectly. And right now, you know, it's hard to say. We've got this little bit. I'm going to leave this up to the students to do this perfectly, but I'm going to say here they start. So now I'm going to go forward and try to find the second honk. Looks like right about there. Well, not the second honk. This is going to be the yell. Let's just confirm this is a yell. That's the yell. And I'm going to mute that one, unmute this one. Alright. So, difference in time. So here, and I'm going to load. Where that loads. Yeah, there is a difference in time. So, you know, this was these things. I said 30 meters apart, but it turns out the horn is about a meter from the laptop, and the laptop's in the car, and the iPhone's not. So there's just several confounding variables, but we'll see how this does. Zoom, zoom, zoom. And I'm just gonna be a little sloppy and just say as soon as I see this thing start growing, say that's the when the screen starts. So 36.770 seconds. And velocity is distance over time. So the distance, in this case, distance is, if I said 1 meter from the car horn, so we've got 1 squared well, this is the difference between the two sources. That's not actually what I want. What I want is the difference in distances. So one of them, the distance is 1 meter. The other distance is 30 meters. So we've got about 29 meters. You can remeasure that if necessary. Okay. Okay. So 29 meters, and distance divided by time is velocity. So the first wave hits at 36.770 seconds, and on this one, well, let's say it starts getting bigger, and this is very arbitrary. I want my sense to do a better job, but I'm going to say that, and I've amplified this, so it's a little harder to say. But let's say it starts looking bigger here, and this is again a little poor, but 36.865, and because we have 44,100 samples per second, I can use all of those significant figures. 1, 2, 3, 4, 5. Yep, 1, 2, 3, 4, 5, 6 figs. So I'm going to say it starts here. Better would be to pick a peak here and a peak here, and now I'll pick that one. 36.880. Alright, close enough. 36.880. Okay, so here I got that the speed of sound, I should have done that the other way, was 263 meters per second. Now if I'd chosen this point as my where the screen started at 36.820, 6.20, well, that doesn't look right. 36.820, then the speed of sound would be 580 meters per second. So really this all makes a big deal about where you actually say the sound starts. I could pick where the harmonization starts, but again, this is going to be a challenge for the students, but they're clearly doing this right. Get this properly. Getting that peak and that peak. We said that this was 36.770. This actually starts getting louder. I'm going to go back with this 36.870, or I can look at this interesting shape here. The peak here looks like a match to the peak here, so 36.805. And here 36.930. 232 meters per second. Still low, so my methods here are not great, and that could be because of how I sync things up at the start. But again, this is just a demonstration. The actual speed of the sound here should be 350 meters per second, given the temperature and then humidity at that time of day, which was recorded. Also, last little bit is we want the harmonization. So let's see if this is what we're hearing the harmony. Zoom out. This area. Not bad. So we're going to analyze that spectrum. It's all within the human voice range, 200 Hertz. So we want to save that. See how the peaks change. Then let's look here. Again, sounds good. Pause spectrum, let's see, I'm looking here at some of the peaks. Let's see if any of the peaks change significantly, and they sure do. This peak at 581 Hertz definitely was the loudest close up, but then far 30 meters away was not so pronounced. So save that. This is interesting data. So then the worksheet that they're going to do, I've also attached, but that's kind of the brainstorming. I've decided to set each experiment into 3 groups. Each group is going to be working on about a 20-foot long table with a bunch of printouts of this whole audio form. And what they're going to do with that is have to sync things up. And they're going to be some questions that make it difficult, such as the mistake I saw before, where there was someone yelling, and I thought maybe it was the car honk. So I'll be there available to play little sounds for people. If they say this little thing here, what is that? So I can either provide the fast Fourier Transform frequency analysis, or I can play them the audio clip so they can know what it is. And they're going to have to figure out some way to average it out and figure out what the speed of sound is and see if it matters to frequency. Alright, thank you for your time.